So yeah, this talk is about making some simulations in some scientific software go faster. And we make it go faster simply by throwing more CPUs at them. And I think it's a nice example because it's sort of the dream scenario in terms of parallelizing something, because it's a pure function that you need to execute tens of thousands of times, like at the same time. And I think it's interesting because it's not as easy as you might think. So I will not be able to tell you exactly what this thing is about because of NDAs and stuff, but basically you have this piece of scientific software. It's scientific in the sense that it does number crunching, and it's nice because it's really you have a pure function that does some number crunching, and then you have to do some statistical analysis basically on it. And to do that, a bit like a Monte Carlo thing. And if you're familiar with that. And to do that, you take this pure function and you need to execute it over thousands of states. I mean, it depends what the exact number is. It depends on how precise you want to be. But it goes from 1,000 to 10,000, right? And actually, let's start this. And yeah, this is sort of like the classic embarrassingly parallel problem that everybody wants to parallelize, right? You're not waiting on any I/O. You're not interacting with any database. You're not. You don't have locks. You don't have mutexes. You don't have any of these problems. But it turns out it's not so easy to get good performance in this scenario. So right, you have this pure function to run it tens of thousands of times. You want to run it in parallel. You have a machine with 18 physical cores. You can rent it on AWS. It's kind of expensive, but it's easy to rent many of them. And the first thing that you might want to try is to use the par primitive that GHC gives you. And this is basically a pure facility, pure in the sense that it doesn't use I/O or mVarts, if you're familiar with that. It just tells GHC execute two things in parallel. And you know, I let GHC do the scheduling and everything. I just want to run to evaluate these two expressions in parallel. And so if you have basically a vector of things that you need to apply a pure function on each of them, you simply, what we tried first is that you split this vector in 18 parts, since we have 18 cores, and then you do a map over these 18 chunks, and you'd expect roughly for each of this piece of computation to run on a separate core, and you should get a 18x speed up, right? But by the way, if you have any doubts or anything, just interrupt me, like raise your hand or shout or something, and I'm happy to take questions. So you try that, and the speed up looks like this. This is actually an old plot. I didn't have time to regenerate something that you could read better. But at the bottom, you've got the number of cores. So you start with 1 and you end with 18. And on the left, you've got the runtime of a simulation. And it starts out with a nice speed up. So going from 1 to 2, yeah, the scale is also weird. It's not a great plot, but it's the only thing I had. It starts with a nice speed up. It actually goes at almost twice the speed, going from 1 to 2. But then it slowly but surely slows down, right? So 4 is not half the time that 2 is, and then 8, and then 12. And around 10 or 12 cores, it just stalls. And worse than that, past 12 cores, it starts to go slower. So you don't get any improvement at all. It gets worse. We actually tried with a machine with more than 18 cores, like a while ago. And yeah, it just gets worse and worse. You basically do not get any speed up past 10 cores. So why is that? Well, some of you, I'm guessing some of you already know why, but the reason is basically garbage collection. And the problem here is that what happens? When you have one core that is executing this function 10,000 times, you're sort of serially going through this list of inputs to process, and you're processing once at a time, and you're generating some garbage, right, that the garbage collector needs to collect. And you've got this this garbage, like this memory is allocated and collected from one single heap. Now, when you add more computation that's happening at once, so for example, when you're running 18 things at once, you're always working on one single heap, right? And the garbage collector will, like, when you're running 18 things, you're generating 18 times the allocations and also 18 times the garbage, right? So the garbage collector basically needs to work much more when you're running this many things at once. And it doesn't it's not quite true. Like the Haskell garbage collector is a bit parallel, and I'm actually not really intimately familiar with it. I'm sure there are people in this audience that know this better than me, but the effect that you get is that as you add cores, you start allocating much more, and that's putting much more stress on the garbage collector. And so the garbage collector needs to kick in more often with longer pauses that end up blocking the work across all the cores, right? I'm using sort of simpler terms here, but you get the idea that basically you need to garbage collect more often and for a longer amount of times, and you block the work across all the worker threads when this happens. This causes like a progressive decrease in the overall productivity of the program, where with productivity we mean the amount of time we spend doing actual work rather than doing garbage collection. So with one core, the productivity is at around 95%. So it's a really healthy Haskell program. You're sort of doing real work most of the time. But then as you add cores, it goes down to like 40%, like around 12 cores. Yes, there is a question?
Is this with the default allocation area?
The nursery? Yeah, we've tuned all the parameters that you can possibly tune. And like also the new, I think it's called N. So it like, okay, so I can get a bit more specific. With a higher nursery size, you delay the problem. In fact, I think that plot was with a 64 megabyte nursery or even bigger, because otherwise it gets worse quicker. So with 512Ks, which is the default, it plateaus much quicker. In fact, I think the default is too low because you gain like 5–10% performance with one thread, but like it's really bad with more threads. So this is it's a known problem, right? It's a known problem that is solved brilliantly by one language in the mainstream, which is this language called Erlang, and it's solved by Erlang by having multiple heaps. Like instead of having one big heap, you have multiple ones. And in fact, there was work, in this direction with Haskell, but it didn't really come to completion. Again, I'm not entirely sure why, but Simon Marlowe was working on these local heaps, but that work was dropped. I hope at some point it will be resumed. So yeah, we have a problem, right? Because we cannot take advantage of this big machines, and more importantly, we cannot just get faster by throwing more resources at the problem, which in some projects is really what you want to do because you have little time or you cannot change the code, and you have this pure function, and like it doesn't make sense. You're like, I just want to run it a lot of times. Why can't I do this? So did I skip? No. So how do we fix this, right? How do we achieve this nice scaling that we want? There are roughly two ways. I would like two general ways to fix it. One is to make this single function, like make the single pure function have less GC pressure, right? You can make the single function to be friendlier to the garbage collector. So if you run it like once, we already know that the pressure is okay. But if you run it 18 times at once, the pressure is unacceptable. If you make it 18 times nicer, right, to the garbage collector, it ought to go fast also with if you run it 18 times at once. So to give you a bit of an idea of what this would look like, in this code base, it's basically vectors of doubles. That's what the state is. And you manipulate, you sort of splice them together, you do stuff with them. But I think like my broad plan to make this function nicer was to have a single pinned state, like a single block of memory that you modify in place, sort of much more imperative, if you will. And you will like drastically reduce this sort of tiny allocations of these tiny vectors that happen all the time in the function as it is now. And this is the best solution, I think, like in terms of like it's a net win. Like this solution, apart from the fact that the code might be a bit uglier, has just advantages, right? It will go faster also with one core. You you might get the scaling for free just using pure facilities like the PAR combinator. So, I mean, it's a really attractive solution. The problem is that, at least in this code base, it would have required like a massive refactor. So this function is a single pure function, but it's like, there are like 70,000 lines of code underpinning it. And we would have had to change the memory layout of this whole thing. So we also are working in like highly regulated industry where code changes have a really high burden of verification. And by the way, this problem is not like, this is like a real world problem that we had to solve. So it's not like we really needed to go faster, quicker in a short amount of time. So yeah, so this was sort of discarded simply because it was too risky in many ways. The second solution, I'm really bad at switching slides today, is to use multiple Haskell runtimes, right? So as I hinted before, the problem in scaling this program is that you're always using the same heap, and this single heap is putting a lot of pressure on the garbage collector. But as I've said, there is a solution to this, which is to have multiple heaps, right? And multiple garbage collector for each heaps. So this is what Erlang does. Each Erlang thread basically has its own little heap, and it garbage collects its own memory, but it doesn't really affect the rest of the threads. And you can really do the same in Haskell. It's just that the facilities are not there to have you to do really easily. And really the only way to do this right now in Haskell is to use multiple processes. So you literally have to spawn multiple worker processes, like not threads. And each process will have a dedicated Haskell runtime with a dedicated heap. And then you need to communicate, to have these processes to communicate somehow, right? But even if it's awkward to do, and I mean, I will explain like also why is it awkward right now? I think it's really the only safe way to do this sort of stuff. And I found it interesting that like a few months later, there was a guy on Reddit which expressed exactly how I felt after this problem. I'm just going to read. For high scalability, fixing GC is unlikely to work. With all the work put into it, the Java garbage collector system is still horrible, while Erlang rules. Isolating heaps and using message passing is more scalable. I'd like to see more work in making multiprocess OS processes programs more fluently. I'm not exactly sure what fluently means, but anyway, I think it's totally right. Like at least with the technology that we have now, garbage collection with one heap and like 30 threads, it just doesn't work. So I also think it would be totally great to have this sort of facilities without having to spawn different processes. But as to now, you need to go through the pain of doing this manually. Another side effect of going this route is that you get for free scalability, like multi-machine scalability, right? If you're using message passing, you basically, there isn't really much difference. I mean, since we also use like sockets to do it, which is the most immediate way to do it, there is no like impediment to distribute it across multiple machines, right? And we do that, and it's just it gives you like much more power in terms of how much you can scale, right? So the next, like the rest of the talk is basically why this is sort of annoying to do in Haskell as of now, sort of what we had to do to make this work. But it does work, so I'm pretty happy with the result because I don't think we would have been able to do it otherwise. So just to describe the problem in a bit more detail, you have this update function which has a state, an input, and it gives you back a new state and an output, right? So again, it's basically literally what it looks like. I'm not simplifying much. It's just a simple pure function. And you have a vector of states, and you need to apply this function to all these states, right? With a fixed input. So you have these initial states, a list of inputs, and you need to repeatedly apply it to the whole, to all the states. And you get a list of, like, a vector of outputs. You basically get for each input a list of outputs. And then these outputs are processed, and that's what we're interested in. And given that, the sort of naive solution is to have worker processes just processing, basically just embodying that function. And all they do is that they take a pair of the state and the input, and they give you back the state and the output, right? So this is the simplest thing you can do, that you have, and we had this at the beginning, you simply have each worker to be a TCP server that accepts these messages and replies. And then you basically implement this parm map. Instead of doing it locally, you send and receive messages to the remote workers. Yes?
So does actually parm map machinery allow you to do that?
No. It's like parm map, but it's not parm map. I'm going to, because parm map is actually not what, it actually executes each element is parallel, which is not good anyway. Because you want to split the workload. You don't want to spark that many computations. So when you do this, the first problem that we encounter is that serialization in Haskell has to now, it's like super slow. It's way too slow for this sort of stuff. And like with serialization in Haskell, I mean binary and serial. This is not like unknown, like it's known that it can be faster, but it was a complete like showstopper for this application. And for us, by far the biggest problem was actually a pretty weird legacy problem of how doubles are encoded. That they're encoded like in a pretty bizarre way that it's just very slow. And we fixed it. Actually, I'm not sure if like with binary, the patch wasn't merged because they need to preserve backwards compatibility, basically in the format. With serial, I don't remember if it was fixed or not. Maybe Niklas does. I'm not sure. Yeah, I don't know. But this, like, after we did this, it was like 5 times faster for our application when we fixed this double problem, and also like a lot of slight problems like unnecessary allocations and stuff like this. But it was still slower than it could be. And so we ended up writing our own library, also because we had another client that needed very fast serialization. And this library is called Store, and it was announced, and and you can use it. I think there was a question, yes. Yeah.
Why is not just a new type of store web in some binary array that will do write serialization for doubles and just put it in memory?
So the question is, why didn't you new type your state, if I understand correctly? I think the question is, you're serializing mostly vectors of doubles. Why didn't you new type these vectors and have like specific instances for those that will be very fast? That is a solution. The problem with that solution is that it's sort of, it has a development overhead whereby you need to be careful about this sort of new types and instances everywhere. And you need to communicate efficiently to everybody in this like 25-person people team that you need to be careful and you need to new type the right thing. Also because the double instance itself is slow, right? Even after that fix, if you just dump what's in memory, it's much faster. Basically, what binary and serial do is that they serialize to big endian to make sure that it's compatible across different architectures and stuff like this. We literally just wanted something that dumped the thing in memory. And I mean, you can do it with these instances, but it's just a bit inconvenient in terms of how developing in like this big team. The other thing is that there are some inherent problems in the state that's carried over by binary and serial when parsing. For example, we never backtrack in store. Like there's just no backtracking. There's no accumulation of bystrings or anything like this. It's just forward. I think anyway, when I actually didn't write store, like Chris Doan and Michael Sloan wrote it, but they also made the basic machinery faster. For example, when serializing, store knows how big the message will be before you serialize it. So you can allocate the buffer to be of exactly the right size before you start actually filling it. So stuff like this. It was just, yeah, it was just easier to start from a clean slate. So yeah, after we switched to store, the serialization performance doubled, and also the memory consumption doubled, like was like a quarter of what it was before. Yeah, store wasn't just for this effort. We needed to do it also because of another effort, but it was helpful for this too. So you make serialization faster. The second problem is that if you're delegating, like if every time you want to evolve a state, you're basically transferring the state and the input to the worker, and then you're waiting for it to come back with a new state and a new input. This is a problem if the state is big. In our case, the state is like in the hundreds of kilobytes, and we have thousands of states. So we have like, considering like the round trips, if we do it this way, you have like gigabytes of data to be transferred at each round of updates. And considering like the time that it takes to actually do the updates, which is like sub-millisecond or like milliseconds, it just still dominated the performance of the program. And so the way you solve this, the way we solved it anyway, was to build a system that can persist the states on the workers. So when you have the initial states, you just upload them evenly across the workers that you have, and you assign a unique ID to each state. And then you do not need to transfer the state each time. You could just say, give this input to state 1, 2, 3, and then give me back the output, because the only thing that you're interested in is really the outputs, right? So you let the workers handle the states, and then there is a master process that sort of orchestrates these updates, and for example, rebalances the states when some workers are idling. The other cool thing about this is that about this rebalancing is that we can add workers at a problem in the middle of a simulation. So if a simulation is running, you can sort of see that it's going slow. We're talking about things that can run for half an hour or an hour, right? You can sort of add things while they're running. And in fact, since there is like in the final product of this thing, there is a web server sitting in front of this simulator. What we can do is that we can very dynamically scale up and down the simulation, like regarding how much we value fairness or how much we value latency. For example, we can say, okay, run at maximum of 5 simulations at once, but then if 3 simulations finish, the other 2 will fill in we will sort of acquire all the workers and start going faster while the simulation is still running. So it's pretty simple, but it works well because, like, yeah, you just have this bookkeeping that you have to do mapping state at these to actual states, to workers, sorry, and then you simply send the inputs to the workers. Of course, this only works if the inputs are very small, which they are in our case. The states are big because, again, they're composed of these big vectors of doubles that represents like curves and stuff. But yeah, it's kind of irrelevant. Now, okay, so results. This is another bad plot, and I apologize, but basically at the far left you see the performance with 8 cores, and the one at the top is the purple curve that you saw in the previous plot. So at 8 cores they're actually similar. So the speed up is it takes a bit to gain momentum. Right now it's not perfectly linear, but then as you can see with 12 cores and with 18 cores, it's like twice the speed. And then you can throw more machines at it. For example, 36 is 2 machines and 72 is 4 machines. And this is also not linear, right? It's clearly not a nice linear curve. We would like it to be linear, and we try to make it linear. But the performance bottleneck that we're hitting now is that the loop that dispatches work to the slaves is not fast enough. So it's just a problem of making this the message passing. The sort of central orchestration program loop to be really, really fast. This is like very common problem, sort of events loop that need to go really fast. And yeah, it's just, there are queues in and queues out. But again, we're pretty happy because we had to change super small part of the code itself to achieve the speed up. And we also got this nice infrastructure where you can throw as many machines as you want at it. Although past 4 machines is not worth it, really. I mean, past 72, past 100 workers, we also plateau. But we plateau at like 100 instead of at 10. So, and I'm confident that we can make it go almost linear if we make that loop faster. We haven't really worked on it much. So I think I'm almost out of time, but I have 2 small asides. So if there are questions, we can answer the question. Otherwise, I have 2 little stories of 2 other problems that I found surprising, but if there are questions, I prefer answering questions because they're kind of unrelated. Yes, Simon. So the question is, that sounds like what Spark does in Scala. Did you consider, I don't understand what I should have considered, migrating to Scala or using Spark as like just to do the orchestration and keep the Haskell layer intact? Right, right. We did not consider it, no, simply because, I mean, I did not consider it, and I was the one like figuring out how to make this go faster. The reason is that I felt I would be quicker doing it this way in Haskell, and I think, yeah, I think I'm right, but sort of I had to know. I mean, this is a fairly simple program in the end, so I sort of programmed exactly what we needed, and I was confident that in the month and a half or 2 months that I had, that I could actually do it. I just saw less unknowns in doing it in Haskell directly. But it's a valid question. I'm also not familiar with Spark, so that's another problem, obviously. Yes?
Did you try using Cloud Haskell for distribution?
Same answer, really. That like, the way this went is that, okay, we have this thing, we need to go faster, right? And sort of I look at it, and like I look at the productivity sort of bottoming out and going like that, and then I program this prototype that does this, and that takes me like 10 days or 2 weeks to do. And since we needed to be sure that this would work, again, like Cloud Haskell, I think solves also slightly different problems, right? But for me, choosing to do it this way, it's mostly about the confidence of being able to deliver it. But it's a very valid question. Like, I also haven't talked about another part of this work, which is actually, there is a job queue in front of this, right? We cannot, if we got 100 simulations, we cannot process them all at once. And that part, I'm not really sure how much I can talk about this in general, but like, I think in that area is much less clear whether you want to invent your own thing or not, because that's solved many times in different circumstances. But for this specific program, I see it more as like, yeah, as a very targeted thing rather than some generic facility. And again, I had never used the Cloud Haskell like in Anger, so that's always a drawback, I think, when you need to do something in 2 months. Yeah. Yes? Like workers failing and stuff like that? Yeah. So this job queue that I've talked about, reschedule failed jobs, and a worker dying mid-simulation is a simulation failure. So basically, you will just redo the whole thing. There is no recovering of lost states because a worker failed. It's just not worth, like, it's just not worth trying to do it. Also because I don't see how you could do it. Like, because you have the inputs that generate the initial states, but the states in the middle of the computation, if a worker dies while it's holding these states, you would have to replicate them somehow, but that's, yeah, you're just better off retrying. Well, if the worker fails, you get an error when trying to send or receive messages from it, right? So I have basically 2 implementations of this message passing, one based on STM and one based on sockets. And I use the STM ones only for testing the correctness of the socket version, basically. But in production, we only use the socket version. So the failure will simply be that, you know, when you do the read, it just fails. Now, of course, if there's a firewall in the middle, then you might get a timeout. But we control the deployment of this. So we know there are no, it's like in the same data center. There shouldn't be firewalls in between, I hope. Maybe there are. If somebody's an expert on AWS, maybe they can tell me. But basically, I just, like, if the communication with work has failed, the simulation has failed. And it will be retried. Anyone else? No? Okay. I don't know if I have more time, but I don't think so. So, okay. I will not talk about the other system. All right, thanks.